Welcome, everyone, to today's Explainer. Over the last few decades, astrophysics has just completely exploded. Thanks to observatories like the Kepler Space Telescope, we've found literally thousands of exoplanets scattered all across the Milky Way. Rocky planets? Turns out they're actually pretty common out there. But all this incredible outward expansion of our knowledge has really just highlighted a massive puzzle right here at home. Because despite billions of worlds spinning through the void, we still haven't found another biosphere. Not a single one. It kind of forces us to turn our attention back to the ground beneath our feet and ask, what is the exact, perfect intersection of geology, physics, and chemistry that even makes our existence possible? Today, we are going to explore the absolute statistical anomaly that is our home planet, and I invite you to join me as we unpack the rare, delicate systems that keep us alive in a seriously hostile universe.
Okay, let's dive into this. The ultimate cosmic mystery isn't just about whether life exists elsewhere, it's about wrapping our heads around the staggering improbability of life existing exactly where we are. Out of all the rocky worlds, the ice giants, and the massive gas behemoths locked in orbit around our sun, Earth is the sole oasis. And guys, this isn't just a matter of random luck or magic. It is the result of a highly specific, totally intricate sequence of astrophysical and planetary events. For a biosphere to actually emerge, sustain itself, and evolve complex organisms over billions of years, a planet has to thread an impossibly tight cosmic needle. And the foundation of that massive balancing act, it begins with our planetary real estate.
In astrobiology, there's this concept called the circumstellar habitable zone, but you probably know it as the Goldilocks zone. Just like the bowls of porridge in the old fairy tale, a planet needs to sit at the exact right distance from its star, not too hot and not too cold, so that water can actually stay in a liquid state on the surface. But maintaining this perfect temperature is incredibly complex. For example, billions of years ago, our sun was actually about 30% dimmer than it is today. By all rights, Earth should have been a giant, frozen, completely uninhabitable ball of ice. Yet early volcanic activity was pumping out powerful greenhouse gases. This created a thermal blanket that held on to just enough heat to make up for that fainter sun. So our position in this Goldilocks zone isn't just a fixed spot on a map. It's a dynamic, evolving relationship between our planet's atmosphere and our star. Now, what's really interesting about this slide is how it highlights three interdependent systems that basically create a closed-loop survival engine. Being in the habitable zone is really just getting your foot in the door. It's what happens next that defines a living world. We're talking about three main pillars: abundant liquid water, a chemically active, breathable atmosphere, and a protective atmospheric shield. And here's the kicker. They absolutely cannot exist without each other. Without the protective shield, solar winds would just strip our breathable air away. Without atmospheric pressure, our liquid water would instantly boil off into space or freeze completely solid. Earth isn't just some bucket holding these three ingredients. It's a roaring, active engine where the deep interior, the surface, and the sky are constantly working together to keep the whole shebang stable. Let's look at that first critical element: liquid surface water. Earth's surface is over 70% water, and we have this continuously active cycle of deep oceans and flowing rivers. That kind of abundance is exceptionally rare. To understand just how fragile this setup is, we really only need to look next door at Mars. Billions of years ago, Mars was actually pretty similar to Earth. It had heavy atmospheric pressure, and we can literally still see the geological scars of ancient, flowing riverbeds and huge lakes carved right into its surface. But Mars's internal core cooled down way too fast. It lost its geologic heartbeat, and because of that, it lost its ability to hold onto its water, leaving behind the frozen, dried-up wasteland we see today. Earth's active, churning interior is the very reason our oceans are still flowing right now. So the crucial point is that just holding on to an atmosphere is really only half the battle. The chemical makeup of that air is what actually drives complex life. Earth's atmosphere sits in the state of extreme chemical imbalance, specifically because it contains about 21% oxygen. And oxygen is super reactive. It desperately wants to bind with other elements and just disappear from the atmosphere entirely. The only reason we have so much of it is literally because of life itself. Billions of years ago, these ancient microscopic cyanobacteria essentially geoengineered the whole planet. Through relentless nonstop photosynthesis, they pumped oxygen into the sky, fundamentally rewriting our planet's chemistry. No other planet in our solar system has this mix. Our breathable air isn't just a random assortment of gases we adapted to, it's a massive, living signature generated by the biosphere. But the absolute unsung hero making all of this possible is our dual-layered planetary defense system. Deep inside the Earth, thousands of miles beneath our feet, there's a molten iron outer core spinning like crazy. This massive subterranean engine projects a powerful, invisible magnetic field far out into space.
It acts like a deflector shield against lethal, high-energy solar winds that would otherwise just rip our atmosphere right off. And working perfectly in tandem with that magnetic field is the ozone layer in our stratosphere, soaking up devastating ultraviolet radiation. Without this dynamic, self-generating defense grid, Earth's oceans would be blasted away into space, and the surface would be completely cold, sterilized, and absolutely lifeless. Honestly, just like the moon.
Let's move to and see how this builds our understanding of comparative planetology. It's so easy to just take Earth's finely tuned geologic and atmospheric systems for granted when we view them in total isolation. But to truly appreciate the incredibly delicate balance of our biosphere, we have to look outward at our closest planetary neighbors. They serve as a stark, empirical reality check of the violent extremes that dictate the rest of the solar system, and they show us exactly what happens when planetary systems completely fail or never even ignite to begin with. And this brilliantly illustrates the drastically different evolutionary paths these rocky bodies took. Think about this. Earth, the Moon, and Mars were all forged from the exact same swirling cloud of dust around the newborn sun roughly 4.5 billion years ago. They started with the exact same building materials. Yet look at the divergence here. The Moon lacks the gravity and internal heat to hold an atmosphere, so it's basically a dead rock swinging violently between hundreds of degrees above and below zero. Mars, despite its really promising watery infancy, suffered catastrophic atmospheric loss, leaving a freezing, irradiated desert with air 100 times thinner than ours. And then there is Earth, a thriving, geologically active heat engine that perfectly regulates its own temperature, holds onto a thick, oxygen-rich atmosphere, and actively supports a booming web of life.
When you fully internalize these planetary mechanics, you begin to experience a bit of a cognitive shift. It's something astronauts actually refer to as the overview effect. The men and women who have traveled beyond our magnetosphere and looked back at Earth from the total vacuum of space frequently report this profound sense of awe. Because against the endless hostile dark of the cosmos, Earth does not appear vast or indestructible. It is famously known as the blue marble. The absolute boundary between a thriving biosphere and the lethal void of space is just a paper-thin, glowing line of atmosphere. It vividly underscores just how rare and remarkably fragile our planetary systems truly are.
The implications of this cosmic reality should deeply reframe how we perceive our everyday lives. Seriously, every time you pour a glass of water, you're interacting with ancient molecules delivered by icy comets and volcanic outgassing over billions of years. Every deep breath you take is a direct inheritance from the relentless photosynthetic labor of ancient microscopic life forms. The things we often view as basic, mundane necessities are actually the extraordinary outputs of a 4.5 billion-year-old planetary engine. The water we drink and the air we breathe are part of an incredibly rare, profound cosmic legacy. They really are gifts. Which leads us to our final thought for today's explainer. We've traced the immense astrophysical requirements, the planetary geology, and the biological engineering that totally separated Earth's fate from the barren worlds right next door. We are sitting on top of a literal statistical miracle of the cosmos. So how will viewing Earth as a rare, fragile blue marble change the way you think about our home today? The next time you step outside, look up and take a breath, I invite you to pause and just contemplate the staggering series of cosmic events that allow you to simply exist. Thank you so much for exploring the science of our incredible planet with me.